P and characteristic P bigger than 0. And if you have any questions, you can put them in the chat and we will relay them to her, or you can politely unmute yourself and ask if you like. So take it away, Monica.
Cool. Thank you very much to the organizers for inviting me to speak today. So this talk is going to be broken up into two roughly equal sized parts. First, we're going to be talking about finiteness properties primarily over the setting of a regular ring with a particular focus on polynomial rings. And in that part one, we're going to be treating characteristic 0 and characteristic P on more or less equal footing. We'll then say a couple of words about what fails as you move away from the regular ring setting. And in part two, we will shift almost exclusively to characteristic P and talk about some attempts to find new finiteness properties that might be productive. So let's go ahead and begin. Oh, sorry, I have to click that. Okay. So to start off with, let's just consider the case where R is a polynomial ring over K, some field in one single variable. So just think for a moment, what would be an example of an operator, say T, that acts naturally on all fractions F over G, where F and G are both polynomials, and has the following properties. So whatever your operator is, I want it to be additive so that it actually deserves the name operator. I want it to preserve R. So if I apply T to a polynomial, I would like to get a polynomial back. And the most important property that I would like is if I take a fraction 1 over x to the n and apply the operator onto it, I would like the power in the denominator to strictly increase, okay? Possibly up to some non-zero scalar in the numerator. So if you sit down and think about it for a bit, there are a couple of different options for T that might come to mind. Perhaps the first one is differentiation, right? If I were to take the derivative of 1 over x to the n with respect to x, I increase the power in the denominator by exactly 1 up to some scalar in the numerator. Though if we're being careful, we said that we wanted the scalar to be non-zero. And if we want this to work for all n, then we are implicitly assuming that the field K has characteristic 0. So what should we do in characteristic P? Well, in characteristic P, there's a particularly natural option for us to choose. That option being the Frobenius homomorphism. So because we're in characteristic P, the Frobenius homomorphism is additive. If you take the Pth power of a polynomial, you certainly get a polynomial back. And if we apply it onto our fractions 1 over x to the n, the power in the denominator does in fact strictly go up. So in either case, we have an operator that is able to kind of increase powers in the denominator in a nice additive way, preserving polynomials. So the upshot of this is this localization, R, where you invert X, is certainly not a finitely generated R module over R, right? If you multiply by elements of the ring R, powers in the denominator can never go up. But we've seen that if you enlarge the ring R by some operator T, where our choice of T might have to depend on the characteristic, we actually do get a finitely generated module over that non-commutative ring. So some non-finitely generated R modules are finitely generated R bracket T modules. So we're interested in this talk in the question of what happens when you augment your ring with a non-commutative operator and what sorts of modules become available to us as finitely generated over this new larger ring. So in characteristic 0, we're going to use a boldface D to denote the augmentation of Q of X. And for the record, absolutely nothing I'm going to say in this talk is harmed by a faithfully flat base change. So if you want to pretend that Q is any field of characteristic 0, that's fine with me. Here we augment with partial differentiation, and D modules for us just mean Q of X modules with an action of differential operators. In characteristic P, our augmentation is Fp of X, where you join the Frobenius operator, the Frobenius endomorphism, where an F module for us, and this terminology is particularly non-standard, so just a little bit of caution, is any Fp of X module that has an action of Frobenius operators. Okay. For the experts, there's an additional hypothesis that sometimes gets baked into the word F module called unitness, which we will discuss later. So for us, F module just means that you can apply Frobenius. Okay. So we've seen that if you invert X, you seem to get a finitely generated module over this augmented ring of operators. What other types of R modules might become available? Well, let's talk just a bit about RFT as a ring before we move further. So it is certainly a non-commutative ring, right? Differentiation does not commute with multiplication by X, right? If I multiply by X and then differentiate, or differentiate and multiply by X, those are not the same operator. Likewise, multiply by X and then apply Frobenius is not the same thing as apply Frobenius then multiply by X. But does this ring have any desirable properties? Can we say anything about the left ideals, the two-sided ideals, perhaps? So to answer that question, it is worth carefully talking about what exactly we mean when we are saying we are adjoining a non-commutative indeterminate. We could think of RFT as being a subring of the ring of endomorphisms over R, but it might be worth looking at it as some kind of abstract presentation, like taking R, adjoining a meaningless symbol, and then imposing some relations. So to start off with, for now, let R be any ring. We'll go ahead and assume that R is commutative for simplicity, but even that is not strictly necessary for some of what I'm about to say. What does it mean to adjoin a formal non-commutative indeterminate T onto R? Well, if you sit down and think about it, there's a couple of meaningfully different definitions that you could come up with. So definition number one, which I'm going to use curly braces for, is you adjoin this symbol as freely as possible. Like no more axioms are imposed than is strictly necessary to get a ring. So for example, monomials like T, RT, and R, T cubed, ST, and so forth cannot be simplified. You have no way to move elements of R past T's in any way. Option two, which is maybe a little bit closer to what we have in mind when we intuitively think of polynomials, is you could imagine trying to make the free left R module on the formal symbols T to the N into a ring. So you want to give this some kind of multiplication law. This has the upshot of all elements of the ring actually look like honest polynomials in one variable, right? They all look like some finite sum of powers of T with coefficients in the ring R. The only thing that we have to do in order to make the latter option a ring is define what a product T times R is, right? Where little r is an element of the ring R. Okay, so we need to know how to simplify that expression and turn it into something of the standard form shown above. And this is a question that has been investigated quite a long time ago by non-commutative algebra people. So Orr, in his paper, Theory of Non-Commutative Polynomials, showed that if you want to put a multiplication on that free module that satisfies a very reasonable requirement on degrees of products, it is equivalent to specify two pieces of data. The first piece of data is a ring endomorphism on R. And the second piece of data is what's called a sigma derivation on R. So if you know the definition of standard derivation, this is just that, but with a twist by sigma. If you don't, then I'll state explicitly what it is. This is an additive map from R to R that satisfies the following sort of product rule. If you want to apply the derivation onto a product RS, then you get something that decomposes like a Leibniz rule, except for the R that comes out on the left has to be twisted by your endomorphism. Once you have those two pieces of data, the multiplication law that you get simplifies the expression TR by commuting the R through T with the sigma endomorphism and picking up some kind of extra debris that looks like your derivation applied onto little r. And the ring as an abstract presentation starts with taking our kind of option one ring, the one in which R is adjoined with the symbol as freely as possible, and then imposes for all little r and R this relation that ensures that you have the right like commutation relation. Note, by the way, that if your endomorphism is the identity and your derivation is 0, this is the usual polynomial ring where T is in the center, T commutes with everything. Okay. So we ask the question, what kind of nice properties does this have? And again, the non-commutative algebra people are very interested in this. And what Goldie showed is that if sigma is not surjective, then this ring that you build using Orr's construction is never a left Noetherian ring. Okay, so if you want the ascending chain condition on left ideals, the endomorphism that you pick had better be surjective. McConnell showed something that is essentially the Hilbert basis theorem. Namely, if sigma is bijective, you have some ring automorphism. And if the base ring R that you started with is left Noetherian, then when you adjoin the extra symbol T onto it, you get yet another left Noetherian ring. And the proof of this statement boils down to essentially the proof of the Hilbert basis theorem in the commutative case, where you're being very, very careful about any step where you might have to switch a T past an element of the ring, okay? So if you have an automorphism, then Leibnithianity is preserved by adding an extra symbol. Okay. So the basic data is a derivation and an endomorphism give us what's called an OR polynomial ring or skew polynomial ring. R adjoins some non-commutative symbol with a certain twisted commutation relation. And this is quite a lot to keep track of. It might be better to imagine simplifying this by taking one of the two pieces of data and making them trivial. For example, you could imagine setting your endomorphism to be the identity and then picking your favorite derivation. In which case, maybe if we were talking about the polynomial ring in one variable, that derivation could just be the partial derivative. And here, the commutation relation looks like if you apply, we'll call our formal symbol y. If you multiply y by some element of the ring R, remember R is just some polynomial, then the R commutes through up to picking up the derivative of R with respect to X. Another thing you can imagine doing is saying like, oh, okay, well, this derivation thing seems like an annoying, like extra piece of information. Let's just set it to 0 and pick our favorite ring endomorphism. And I don't know about you, but my favorite ring endomorphism is the Frobenius. So in that case, what we would get is R adjoin a formal symbol where when you multiply by Y, you're allowed to commute elements of the ring through by taking their powers. So on the left, the identity map is always a bijection. Exercise is left to the reader, which means that by the Hilbert basis theorem, regardless of what our derivation is, we get a Leibnizian ring. Note, however, that in characteristic P, the differentiation with respect to X is a nilpotent operation. So we're not particularly going to get a lot of mileage out of the construction over here. So we'll mainly focus in that column on the characteristic 0 case. To give like an extra remark to experts, while you can always adjoin this extra derivation on, this doesn't actually give the object that deserves to be called the ring of differential operators if you're in characteristic P. This is only the ring of differential operators in characteristic 0. Now, concerning the ring on the right, when is the Frobenius surjective? So let's say that we wanted that Noetherianity result. Well, the ring of Frobenius, the Frobenius map is surjective if and only if your ring is a product of perfect fields. So for essentially all commutative rings that we are going to care about, this ring of Frobenius operators is essentially never Leibnizian, okay? So the question that is probably on your mind right now is, isn't this supposed to be a commutative algebra seminar? Why do we spend so much time talking about non-commutative rings? And the answer is because commutative algebraists actually care quite a bit about these two rings. So our ring of Frobenius operators and our ring of differential operators, where remember, I'm only allowed to use that phrase ring of differential operators for this if we're in characteristic 0, or some version of it where we adjoin a set of K derivations, perhaps some linearly independent basis for the module of K linear derivations. So the left ring, the ring of differential operators, first made its debut in commutative algebra in a paper of Lubeznik in 1993. We'll talk about what Lubeznik's motivation for that was in a moment. And as far as commutative algebraists are concerned, Frobenius actions have been around for quite a long time. It would actually be a rather difficult task to trace their exact historical origins, but at least the first person I can find in the literature to explicitly talk about this non-commutative ring in the language of non-commutative algebra, writing up this presentation, seems to be a paper of Yoshino in 1994, whose interests were in the context of tight closure, which is certainly something that commutative ring theory people care about. So if you don't know, tight closure is a theory of Hochster and Hunicke, which is kind of like the poster child of results in commutative algebra that are clearly of algebraic interest and do not on their face involve the Frobenius. So there are a number of statements like direct summands of regular rings being Cohen-Macaulay, for example, or regular rings splintering as direct summands of module finite extensions, which sound like they have nothing to do with the Frobenius, but using this tight closure theory, you actually can get quite a lot of mileage on proving those. So what Yoshino showed is that tight closure has a relation to structure as a module over this non-commutative ring, where he describes how tight closure is essentially about annihilators of principal right ideals and gives some results on tight closure in that kind of language. This is not, I'm saying, the main way that people think about tight closure theory, just a historical kind of debut of this ring. Now, going back to the left column over here, Lubeznik's interest was in something called local cohomology. And incidentally, local cohomology was also the motivation for an introduction of this ring of Frobenius operators into commutative algebra that seems to be kind of parallel and independent to Yoshino due to Lubeznik and Smith. So our main interest in this talk, how do these non-commutative rings tell us interesting things about commutative algebra, is going to be how do these non-commutative rings tell us about local cohomology? Okay. So to start off, what is local cohomology? Well, the local cohomology of R, denoted H superscript I sub I of R, where I is some ideal, is the ith cohomology, ordinary sense, kernel of one map mod image of the previous one, of the following complex of localizations, where you're taking the direct sum of R localized at one element as F ranges over some set of generators for the ideal, mapping that to the set of localizations of R in all pairs of elements, and then all triples of elements and so forth, with appropriate signs to make this actually a complex. And this is not obvious, but it turns out that the cohomology of the complex does not depend on your choice of generators. In fact, it doesn't even depend on the choice of generators up to radical, which is pretty cool. So local cohomology tells us a lot of very interesting properties about the ring itself. It encodes information about Cohen-Macauliness, the Gorenstein property, regularity can be found in there. So this is certainly an object of interest to us. Now, what we're interested in here is about the structure of local cohomology, either as a D or F module. So just to start with an example of a local cohomology module, consider taking the polynomial ring in two variables over a field and forming top local cohomology, H superscript 2, with respect to the homogeneous maximal ideal xy. So as a vector space, this is not too hard to describe. It has basis 1 over x to the I, y to the j, where I and j are positive integers. So it kind of looks like this upside down pyramid sort of thing, again, just as in terms of vector space bases. And as a module over k of xy, the action of x increases the degree in the denominator, or sorry, increases in the sense of making it less negative, moving you up in that direction, where if you fall off the edge, you die. And multiplication by y moves you in the other direction, where again, if you fall off the edge, you die. Okay, so this is certainly not a finitely generated k of xy module, right? If you were to pick any finite number of elements of this, they're going to involve monomials with bounded degree. Multiplication by x and y will never move you below that degree, so no finite set of generators will suffice. However, we can pretty reasonably put a structure of either a D or F module on it. So for the sake of drawing pictures, let's suppose we're in characteristic 2 and we want to apply Frobenius onto elements. Well, imagine just taking, for your action of F, grab any monomial on here and then apply Frobenius, just square it, right? So all of these go down to the following, right? 1 over xy goes to 1 over x squared y squared. 1 over x squared y goes to 1 over x to the 4th y squared, and so on and so forth. So applying Frobenius moves you down in the pyramid, right? That was the main thing you were lacking when you were trying to get finite generation over R, is the ability to move down. And how do D-module actions work? Well, what does partial differentiation by x do? It takes your monomials and it shifts them backwards along the x direction, right? Your x degrees become more negative, up to some constants in the numerator that would vanish if you were in characteristic P, where some of them would vanish. Differentiation with respect to y takes a monomial and then moves it backwards along the y direction. So between these two moves, the ability to move backwards along the x direction and backwards along the y direction show pretty clearly that if you start with this 1 over xy class, then you can get to any monomial that you like by some combination of differentiating with respect to x, differentiating with respect to y, multiplication by x, and multiplication by y. So again, we see that we get finite generation over the ring of differential operators here. And in fact, if you were to sit down for a bit and try to show it directly, you would not have a super tough time proving that if you take your polynomial ring and n variables and form top, that is to say local cohomology with superscript n, cohomology with respect to the ideal generated by x1 through xn, so that's the homogeneous maximal ideal, you get a finitely generated module either over the ring of differential operators and characteristic 0, or the ring of Frobenius operators and characteristic P. It is in fact a cyclic module where the generator is just the Čech cohomology class 1 over the product of the x's. And this can be proven in a very direct way. The bases look like a natural generalization of the basis we showed on the previous slide, and just either repeated differentiation or repeated application to the Frobenius can get you from this one element to any element. Okay. Now, where it starts to get a little bit harder is if you ask, okay, that's top level cohomology with respect to the x's. What about general top level cohomology, where the denominator might be some product of f's being arbitrary polynomials? Well, in characteristic P, nothing about the argument changes. Taking pth powers increases the powers of f's in the denominator. And if you think about it, you can still take that one single Čech class, 1 over the product of zf's, and get to any other Čech class you like, moving through appropriately with Frobenius and multiplication by the variables. But it's far less obvious what to do in characteristic 0, right? If you take a 1 over the product of the f's and try to differentiate it, you're going to pick up by the quotient rule extra stuff in the numerator that's not so obvious how to get rid of if you want to form 1 over the product of the f's to a higher power.
Oh, there's a question.
Yes.
Is the minimum number of generators 1 in the example of top local cohomology and polynomial ring of dimension 2?
Is the minimum number of generators 1 for top level cohomology in dimension 2? As a D or F module, yes. I mean, you certainly can't get away with 0 generators. I might be misunderstanding the question. What you mean by minimum number? If you mean like, does that continue to hold for non-top local cohomology? That's actually an interesting story for holonomic stuff in characteristic 0, and in characteristic P, I don't actually know the answer, but I'm inclined to say probably no, it's not always 1 generator. Does that answer the question?
Yes, he says yes.
Okay, cool. Okay, for top local cohomology with respect to any number of f's, 1 generator is always enough in characteristic P. It's far less obvious that it's even finitely generated in characteristic 0. As far as non-top local cohomology goes, where this is going to be some very complicated object that has to do about syzygies on I tuples of various powers of the f's, modulo trivial Cazul syzygies, and then some stabilization about a map into the direct limit. It's not obvious what a finite set of generators would be for this, either in characteristic 0 or in characteristic P. Okay. So taking a look at this, we might ask, does finite generation always hold? Are we able to get some kind of property for these modules, or property for finitely generated modules over our rings of operators that give us better control over local cohomology, which on its face in the non-top case for arbitrary polynomials looks like something that is potentially quite formidable? Well, if our goal is to show that arbitrary local cohomology is finitely generated over either a ring of differential or Frobenius operators, I claim that it would be enough to have the following. So first off, we would like R to be finitely generated. That's easy. Second, it would be nice if finite direct sums of finitely generated modules are finitely generated. That too is easy. The 2 hard things that we're going to ask are, can finite generation of a module be preserved when you localize that one element? And if I have either a D or respectively F linear map between finitely generated modules, must the kernel and co-kernel of that map also be finitely generated? For co-kernels, this is easy. For kernels, let's be a little bit careful. Over D, which is left Noetherian, we're good to go. The kernel is a submodule of a finitely generated module and therefore finitely generated. For F, which is basically never left Noetherian, this is quite concerning to us. In fact, as stated, it's impossible, right? Because it's left Noetherian, there have to be kernels of F module maps that are not finitely generated. And then the finite generation preserved by localization at one element Some modification of the Frobenius trick that we discussed seems like it might be promising in characteristic P, though there's still a fair amount of work to do. But in characteristic 0, we didn't even know how to proceed if you were just localizing the ring at one element, much less an arbitrary module. So unfortunately for us, getting the 4th bullet regarding control of kernels is too much to ask over F. And getting the 3rd bullet, finite generation of localizations of a finitely generated module at one element is asking too much over D, okay? So we kind of need to replace finitely generated over here with so-called finitely generated plus, like the deluxe subscriber version of finitely generated that you have to pay like $15 a month for. So local cohomology modules are not random finitely presented or finitely generated modules over D or F. They're very special modules that are built in very special ways. So it's possible that finite generation of kernels is impossible for arbitrary finitely generated F modules, but maybe for local cohomology and the natural maps that arise between local cohomology modules, there's still something we can do. Maybe it has some extra bonus property besides just being finitely generated that will save us. Okay, so what might that property be? Well, let's start by talking about the characteristic 0 setting. So if we just kind of go back to basics and try to imagine, like, right, we're talking about finitely generated modules over a ring, a non-commutative ring, I guess. If we just try to build up the classic theory of finitely generated modules, we're kind of forced in some ways to see the need for these additional niceness properties. And historically, in the development of the theory of finitely generated modules over here, various authors have come up with the niceness conditions that are necessary. So for characteristic 0, let's discuss that first. So take R a polynomial ring over Q or any field of characteristic 0, and recall our ring of differential operators where you adjoin the symbols partial 1 through partial n that satisfy relations where they commute with each other and they commute with the variables in a special way. Or rather don't commute, but their commutator is special. Sorry, I misspoke. Okay. So suppose that we have a finitely generated D module M. Again, let's just try to think in terms of what finitely generated modules over a ring mean. That means that we can surject a finite direct sum of copies of D onto M. And this is a Lefnerian ring. So whatever that finitely generated, or those finite list of generators for M will be, this map is going to have some kernel. That kernel is going to have to be finitely generated. So there's a finite generating set for the syzygies, and we can imagine surjecting another direct sum of finitely many copies of D onto that kernel to extend this backwards to an exact sequence, exactly how would we do it over a commutative ring, and kind of continue onwards indefinitely, right? We can try to build a free resolution for M as a D module, which is certainly something that we would want to do in the commutative setting. And thinking in terms of the commutative setting, the natural question that you would want to ask is, does this ever stop, right? Is Hilbert's syzygy theorem true? Is there some like bounded global dimension that will tell us we're done past some point? Interestingly, the answer is yes. So there are, as far as I can tell, 3 more or less independent proofs of this due to Reinhardt, Roos, and Kashiwara. Reinhardt and Roos approach it from more of a non-commutative algebra lens, whereas Kashiwara's approach is somewhat special, and I'll talk about it in a moment. And what they show is that if M is a finitely generated D module, then it will have a resolution of length no more than 2n by finite rank free D modules. Now, I said that I want to single out Kashiwara here. So Roos and Reinhardt gave this statement in somewhat fuller generality, but in a sense, Kashiwara's result is more interesting because while Kashiwara only proves this result for a very limited class of D modules, that class of D modules kind of sits at the heart of our current understanding of like D module finiteness theory. And that class is what's called holonomic D modules. So let's talk about Kashiwara's notion of holonomicity. Just recall in terms of commutative rings only that a finitely generated R module is called Cohen-Macaulay of dimension D. Here R is our polynomial ring unit variables say, if and only if all of the X modules from M to R vanish for I not equal to n minus D. Okay, so we can give a description of Cohen-Macaulay in terms of this vanishing of X conditions. So there's a wonderful Cohen-Macaulay type condition introduced by Kashiwara called holonomicity, which says that a D module is holonomic if all of the X over D, where how do we understand that X? Well, we have a free resolution of M, and you can apply holomon to it and then take cohomology, vanish for I not equal to 2n, which we can kind of think of as quote unquote the dimension of D, where dimension might even be in a purely formal sense, like just the number of symbols that we need to generate it, although we can make it more formal if we want, minus n, okay? So holonomic kind of means Cohen-Macaulay of dimension n in a vague sense. What's the upshot of this? Well, just as a brief note before we talk about the upshot, the ring R is holonomic, the ring D is not. So holonomic, it turns out, is in a sense kind of a smallness condition, and D, the ring of operators, turns out to be too large. So R is holonomic, D is not. But okay, what is the upshot of holonomicity? Well, holonomicity turns out to be exactly the right kind of finitely generated plus condition that we want over our ring of differential operators. So not only is Kashiwara able to use it to study these Fs and prove things like Hilbert-Syzygy's theorem, he's able to show that, well, the ring itself is holonomic, that finite direct sums of holonomic modules are holonomic, that if you take a holonomic module and localize that one element, you get a holonomic module, and that co-kernels and kernels of D linear maps between holonomic modules are holonomic. So this property has exactly the things that we want off of our wish list, in addition to many more highly desirable things that are not relevant to the immediate discussion. Okay, so for us, the niceness condition in characteristic 0 is holonomicity, which is a strengthening of mere finite generation. What about for characteristic P? What should we do? Well, let's try to play the same game. Suppose that I take a polynomial ring in n variables over Fp or any field of characteristic P, and we look at our ring of Frobenius operators. Here, this is just Fp adjoint variables plus one extra symbol F that satisfies a commuting relation where variables get P powered when they move through. And suppose I hand you a finitely generated F module M. Again, finite generation means that I can surject a finite direct sum of copies of F onto it, but F is not finitely generated, or sorry, is not left Noetherian, so we are out of luck past that point. In general, it's possible for that finite list of generators to have an infinite list of syzygies, and we can go no farther unless we want to break the finite rank condition. So if we want to get out of that trap and recover something that even vaguely resembles a theory of finitely generated modules, we're going to need additional tricks. And the current state of the art for this, the best way to get control over F modules is to impose an extra condition originally due to Lebesgue called unitness. So to define unitness, let's let mathcal F, curly F, calligraphic F, denote the base change functor along the Frobenius endomorphism. So it turns out, and you kind of would have to just sit down for a bit and play with what it means to base change along Frobenius to really see why this is true. So I'm just going to assert this, that an F module structure on M is equivalent to giving an R linear map from the base change of M to M. If you just write down what F mapping from M to M does, like what the action of Frobenius does, and try to make that into an R linear map, you'll see that some kind of base change ends up being necessary, and this is just the structure map that is necessary. So we call this the structure morphism of the action of F on M. Now, why is this a useful perspective? Well, this base change functor for the types of rings we've been discussing, which thus far have been polynomial rings, but could have just as well been arbitrary regular rings, has very nice properties due to a theorem of Kunz. So what Kunz showed is that if you give me a Noetherian ring of characteristic P, that ring is regular if and only if the Frobenius functor is exact. So this kind of gives us two statements that we can use at once. Number one, it says that if we're dealing with the regular ring, we have this nice exact functor here that will help us get control over kernels in a way that's hopefully not too much of a stretch to see, right? Having that extra 0 on the left is going to buy us quite a lot when we're trying to show that unitness passes to the kernel of an F linear map. On the other hand, it also comes with a stipulation that we'll talk more about later, which says that if R is singular, necessarily your trick must fail. The Frobenius is no longer allowed to be exact at that point. So we have to kind of keep that in mind, that this is a very special thing about regular rings. But indeed, just to kind of put this like criteria that we're about to impose in some context, something that you might want to recall or learn from the first time. This is something of an obscure fact, and for me, this was a learning fairly recently. A finitely presented R algebra is étale if and only if the structure map of its Frobenius action, we're assuming we're in characteristic P, is an isomorphism. So there's a wonderful étale type condition that I think is originally due to Lubeznik that we call an F module unit if its structure morphism is an isomorphism. And once we have this condition unit, we're able to regain a lot of the control that we were missing for arbitrary finitely generated F modules. So like in the holonomic setting, we have that the ring itself is unit. It has our finitely generated plus condition, whereas the ring of operators does not. And like in the D module setting, we get a whole bunch of really nice things that wouldn't have been available to us otherwise. For example, Hilbert-Syzygy theorem, which is, I think, originally due to non-commutative algebraic techniques, a result of Kuhn's working over like a setting where he doesn't even work with Frobenius. He's just assuming that things kind of commute through in a special way that ends up kind of yielding this result as a side effect. For the Frobenius in particular, this is due to Lubeznik. And then a more explicit statement can be found by Emerton and Kaysen. If you start with a unit F module, then it is possible to give a resolution by finite rank free modules. And I want to just pause to comment that this is a fairly underrated part of Hilbert-Syzygy theorem, right? Not just that the resolution stops, but that the ranks of everything in between are finite rank. But also, after you continue that process, it does stop eventually. In this case, the maximum length is n+1, which again kind of feels like the number of variables that we're dealing with, all of these x1 through xn's plus our symbol f. Okay. And Lubeznik shows unitness turns out to be exactly the kind of condition that we want. So the ring itself is unit, finite direct sums of unit modules are unit, localizations of unit modules that one element are unit, and kernels, co-kernels of F linear maps between unit modules are unit. By the way, I'm just going to go back a slide to make one comment real quick. I'm going to, just for simplicity in the scope of this talk, take a non-standard definition here where I assume that finite generation is part of the hypothesis of unit. So some authors, probably most authors, would say the phrase finitely generated unit module. Just for simplicity in this talk, I'm going to assume that finite generation is baked into unit. So just keep that in mind. But okay, so let's talk about the kind of summarizing picture of what we have for our modules that are finitely generated plus an extra niceness condition. So on the left column, we'll talk about the characteristic zero setting, where a lot of the work originates due to Kashiwara, but many of the results that we're going to assert appear originally from Bernstein, Mepkut, and towards the bottom, Lubeznik. And then on the right, a lot of these arguments are first explicitly laid out by Lubeznik in 97, but the core of some of the arguments can be found in Hunicke and Sharp from 93, or from Hartran and Spicer 77. And then of course we talked about Kuhn's theorem as kind of necessary to get this whole field of exploration up off the ground. So on the left, we have polynomial rings of characteristic zero. On the right, we have polynomial rings of characteristic P. And as one more remark before we state the upshot of this, on the right, if you wish, you could replace R with any regular ring. On the left, I do not believe any regular ring of equal characteristic zero is legal yet. However, regular affine algebras are allowed. Regular local rings of equal characteristic zero are allowed. So there's some kind of complications that come in here if you want this to work for arbitrary regular rings. But okay. Over our ring R, we have a distinguished ring of operators, either differential operators or Frobenius operators. And we have a niceness condition that is a strengthening of finite generation, either holonomicity or unitness. Our niceness condition is closed under a number of operations, such as localization at one element, finite direct sums, kernels of linear maps over our ring of operators, and co-kernels. And by iterating those previous operations, it is closed under arbitrary local cohomology functors. So kind of as a side effect, we not only get that our property holonomic or unit, which recall, answers our original question of finite generation, since these are both encode finite generation into them. Not only is local cohomology going to have this nice property, but even iterated local cohomology will have it. If you take a local cohomology module and apply another local cohomology functor, you still get a holonomic or unit module. And okay, that's all well and good. You get a nice module with some nice conditions that is finitely generated over some kind of strange ring. What does that imply? Well, it implies a great number of things. Most of these results can be found in one of the two Lubeznik papers, or except for Hilbert-Syzygy theorem. That one is either Kashiwara or the Emerton and Kyson in characteristic P. You can have Hilbert-Syzygy theorem. ACC and DCC are the big result from the two Lubeznik ones. So they are finite length in the category of holonomic or unit modules. Note that in the characteristic P setting, this is only ACC and DCC on unit F submodules, not on arbitrary F submodules, where for D modules, this is ACC and DCC on arbitrary D submodules. So just one distinction to make there. As a fairly immediate consequence, you get finitely many associated primes, which is a very big deal for studying kind of the commutative algebraic properties of these local cohomology modules. It implies, for example, that their support is the Zariski closed locus. You have finite Bass numbers, which is kind of very surprising that works out. But in addition to finite Bass numbers, when we're looking at the injective resolution, we also know that the injective dimension is something that we can control. It is no more than the dimension of the support, it turns out. So our niceness condition turns out to imply many nice things. We not only get excellent control over these local cohomology modules, we get a number of excellent properties over them. Now, how much of this is going to hold if we try to move from the regular setting to the singular setting? Well, like I said, there are a few hiccups even moving from the regular setting to the slightly different regular setting in characteristic 0, right? If you want to move from polynomial rings to arbitrary regular rings, like not necessarily local, but kind of ignoring that, the problems become much, much worse as soon as you drop regularity altogether. So first off, we should say right away that we should not expect anything nearly this nice. The rings of differential and Frobenius operators are at least still both defined. The ring of Frobenius operators has exactly the same definition. You adjoin a formal symbol F and impose some commuting relations. The ring of differential operators has a definition that is much stranger if you've never seen it before, involving iterated like kind of commutator constructions. And one consequence of the kind of weirder definition, it is not really clear what holonomic should mean in the general singular setting. The standard definition of holonomic involving what's called the Bernstein filtration no longer makes sense at all. There's not necessarily a Bernstein filtration for an arbitrary singular ring. And the Ext definition falls apart because we turn out to lose left Noetherianity. So those free resolutions are not going to be nearly as behaved. It's much harder to get any sort of vanishing conditions on forming X from them. Yeah, so D is not a left Noetherian ring anymore. I think that it is actually conjectured that, and a D module expert can correct me if I'm wrong, that the ring of differential operators being left Noetherian implies regularity. I think that is a conjecture. I don't know that for sure, but I know that the standard expectation is if you give me a general singular K algebra, I should not expect its ring of differential operators to be left Noetherian, and most examples are going to be that case. So as an upshot of that, control of kernels become a serious issue, and even just localizing the ring at one element becomes a serious issue due to an example of Bernstein-Gelfand that does not have to be finitely generated over the ring of differential operators. So between not being able to take kernels and not even being able to localize the ring at one element, trying to get anywhere for finite generation of local cohomology is a huge problem right away. Unitness can still be defined over F. So we still have our Frobenius functor. We can still insist that the structure map is an isomorphism. We can still try to prove things about that. But again, Kunz's theorem says that if you're not regular, then necessarily that Frobenius phase change functor is not exact. So unitness is no longer going to pass to kernels. And if we can't pass to kernels, then we're going to have a very hard time getting any useful statements about non-top local cohomology. Although if you're noting carefully, top local cohomology does not require such a thing and is going to go through just fine. And it's not just an issue of trying to get our definition of niceness to make sense. It's that we can't possibly hope for the nice properties towards the bottom of the table on the previous slide to work. It is known for a fact that the set of associated primes, even of top local cohomology, does not have to be finite anymore. So we kind of know that we can't get too much out of this, right? We can't really expect finite length in a sufficiently useful sense to hold, because a sufficiently useful kind of finite length condition would imply finiteness of associated primes using an argument exactly analogous to what Lubeznik does. And if the associated primes set does not have to be finite, then that can't work. Okay. So if we try to rebuild our table of how the picture looks for the general case of singular rings over either field of characteristic 0, field of characteristic P, I'm not saying a word about mixed characteristic at the moment. And I'm also talking at the general level, what can be said about all arbitrary singular either Q or FP algebras. So there are special classes where this can be made a little bit stronger, but let's talk about the general setting. In both cases, we do still have a general ring of operators that we would like to give local cohomology the structure of, and it does have the structure of it, just doesn't have very many niceness properties over. Either the ring of differential operators or the ring of Frobenius operators. For the characteristic P setting, we do have a niceness condition called unit that kind of comes built in with a guarantee that it must not behave too well due to Kuhn's. In characteristic 0, it is unclear what holonomic should mean outside of some very special cases. So the best we can try to use is just finite generation, which we kind of know to be inadequate. And in either case, if we take our niceness condition using finite generation as a stand-in in characteristic 0 or unitness in characteristic P, we don't get enough to get local cohomology. Localization at one element, totally fine. In characteristic P, it turns out that's not quite trivial to show. That unitness, which remember we're taking to encode finite generation, passes from one module to another after localizing, but it does work. For characteristic 0, this is known to fail. Finite direct sums are easy. We can check that one off our list and pat ourselves on the back. Kernels fail in both cases. These are not Noetherian rings. And even for unit stuff, again, the failure here is due to Kuhn's theorem. Co-kernels, again, not too bad, nothing to worry about. The fact that Frobenius is right exact at least gives us co-kernels for unitness and characteristic P. But because we can't get the localization at one element or in the characteristic P setting, we can't get kernels, our ability to preserve finite generation after taking arbitrary local cohomology functors does not go through. Now, I'm using a weird font color in characteristic P because in characteristic 0, there are known examples where this local cohomology functor creates a non-finitely generated module. To the best of my knowledge, and I would be thrilled if someone in the chat happens to know of an example that will prove me wrong, I do not know of any published examples of a local cohomology module in characteristic P that is definitively not finitely generated over the ring of Frobenius operators, or definitively not unit. It seems too good to be true, but the infinite associated primes examples are not quite good enough. Like all that unitness in general is going to buy you is close support, but it does not guarantee you finiteness of associated primes. So those aren't enough to rule out the possibility that local cohomology could have this property. I suspect that this is too good to be true, but I don't know of an explicit counterexample. One thing worth noting, though, is that top local cohomology, which does not require you to take kernels, does have this property. In characteristic 0, you do not get finite generation as a D module, again, using the Bernstein-Gelfand example. And does our nice property imply nice things about the module? Well, in neither case does it necessarily imply finitely many associated primes, but in both cases, it does imply close support. So particularly in characteristic 0, there's a very limited number of things we can actually do while preserving finite generation, but at least what you can do does preserve close support for modules. And in characteristic P, this is able to get some fairly non-trivial results. One due to, it's in a paper of Katzmann, he attributes the argument to Lubeznik, showing that top local cohomology has close support. And on the next slide, we'll talk about some more kind of sophisticated arguments by Hochster and Nunez-Betancourt, or by Katzmann and Zhang, that get various closed support statements over different modules in characteristic P. So to kind of summarize the table in the singular setting, our niceness property is preserved under fewer operations, and it does not bias as many nice things. Okay. However, there is still some reason to hold out hope that an undiscovered finiteness/niceness condition may be lurking out there, and we just don't know what it is. The reason that you might have some hope left is that, and this is especially true in characteristic P, local cohomology modules still seem to, even in the singular setting, hold on to some really nice finiteness properties. There is evidence suggesting that these tend to have closed support. No known counterexamples exist. Like we do not know of any local cohomology modules, even in mixed characteristic, that definitively have non-closed support. And we know of many examples where the support definitely has to be closed, which I'll summarize briefly in this table and not read through in detail. But suffice it to say, people have looked hard. And in every case that we're able to get definitive results on, closed support has turned up. And in characteristic P, we consistently seem to get better results. We are able to prove more closed support conditions than we're able to in the characteristic 0 case, kind of due to that table having more things that we're able to do with top local cohomology than we are in the characteristic 0 setting. So looking at this picture, we know of a lot of local cohomology modules over large swaths of singular rings, at least under appropriate conditions on the ideal or on the cohomological degree, where you get finiteness conditions that look like finitely generated modules. So maybe there is some underlying condition that's driving this. To ask kind of more concrete questions, is this actually a genuine phenomenon, or are these just coincidences? Does local cohomology module always have to have closed support? Or is it just that we've only been able to kind of prove it closed support for the cases where things work out nicely in our favor? Might there exist counterexamples to this out there? And supposing that we restrict to characteristic P, remember in characteristic 0, we know that finite generation can't hold, which makes it kind of hard to think what the finiteness condition should be if it can't be finite generation of the ring of differential operators. Maybe you need a smaller ring of operators, maybe you need a different ring of operators altogether. So pose this question in characteristic P where we at least have our ring of operators that we prefer, and we haven't been able to rule out finite generation. Well, we could ask, is local cohomology always finitely generated? If that's true, that would certainly imply closed support, and it would explain why we keep seeing closed support come up in all of these different settings. Is it finitely generated plus in any sense? We know unit is not likely to work out for us, and Kunz's theorem says that we really should not hold out hope. It kind of necessarily has to fail for sufficiently general classes of maps. But might there be some condition like unitness, or maybe very different from unitness, that we can staple onto finitely generated in order to obtain like a control over localizations, over kernels and so on, and perhaps recover closed support that way? And what would that condition be? What should finitely generated plus mean in the general characteristic P setting? So we're going to call this the end of part 1 of this talk and take a little bit of a break. And in part 2, I'm going to talk about some kind of preliminary work looking at maybe a plus condition that could potentially lead somewhere in the characteristic P setting, and give us a class of modules that we might try to show that local cohomology has these properties. The preliminary work still being over a polynomial ring, but being sufficiently different from unit that we have some hope that it might get us at least somewhere in certain classes of singularities. So if there are any questions from part 1, I'm happy to try to answer them. And if not, then we can take a 10-minute break or so and continue with part 2.
We could do just, we usually do 5.
Oh yeah, that's fine.
Is that okay? Okay.
Yeah, totally.
Okay. So are there any questions? Please unmute yourself if you have any. I think we're mostly just curious to see what is your proposed condition in characteristic P.
Let me just pull up the
Oh, yeah.
part 2 slides real quick. Cool. Are you able to see my screen? All right, ready to go whenever you're. Okay, so welcome back to part 2. We are going to continue talking about finiteness properties of local cohomology and characteristic P. And this is the half of the talk that is going to be almost exclusively characteristic P. So previously we had characteristic 0 and characteristic P kind of split left and right on almost equal footing. And here the asymmetry is going to be leaning pretty characteristic P heavy. Okay. So broadly speaking, our goal is to look around at things that could possibly work as new niceness properties to staple onto finite generation in order to get some control over local cohomology that finite generation alone doesn't convey to us due to the lack of Noetherianity, for example, and that unitness alone doesn't convey to us due to, for example, the failure of Kunz's theorem. So unitness, remember, is the condition that works well over that fails to work well over singularities of characteristic P for a fairly fundamental reason. Kunz's theorem guarantees that the base change along with Frobenius is not an exact functor anymore. And it would be nice to have something that is an extra kind of niceness condition that does not as explicitly rely on the behavior of the Frobenius base change. So is there another way to kind of characterize niceness that does not rely on the description of that functor? So in this talk, our goal is to ask whether there might be something like holonomic for modules over the ring of Frobenius operators. And something that I want to clarify right away is just deconflicting with terminology in the literature. Is Bott and Lurie in 2017 give a class of F modules that they call holonomic, and this class of modules has excellent behavior. It has a Riemann-Hilbert correspondence. It has essentially any nice property you could ask for. It even works over any commutative ring of characteristic P whatsoever. It doesn't even have to be a Noetherian ring. The reason that we're kind of stepping outside of that context here is their class of modules does not include the ring R itself or its localizations, unless I'm severely misunderstanding how their theory works, in that their version of holonomic only works for perfect F modules. Now, it is an open question whether there is a way to deal with, for example, the perfection of local cohomology and whether that might be holonomic in this sense, and whether you could extract finiteness properties of local cohomology from the Bott and Lurie notion of holonomic. But the kind of limited question that we're going to be interested in is there maybe some notion of holonomic? We're not going to ask as much. We don't even want finitely many associated primes for our notion because we know we're not going to get it. We certainly aren't going to ask for a Riemann-Hilbert correspondence or anything such nice, but can we find something nice-ish that at least works for local cohomology, which are highly non-perfect in both the technical and the non-technical sense of the word? So to kind of ask what that is, it's worth sort of asking like what holonomic means. So historically, holonomic is a term that comes from classical mechanics. If you've taken a class on like Lagrangian mechanics, you might have heard the term holonomic constraints before. Or in terms of systems of PDE, this is at least the terminology Kashiwara uses. I don't know if there are other more standard terminologies. He calls them maximally overdetermined systems of linear PDE. And in both contexts, what holonomic boils down to is that some kind of characteristic variety is defined. And holonomic means that the characteristic variety has minimal dimension, where the minimum ends up being something non-trivial, either due to like Lagrangian structure on the configuration space of mechanical system, or due to deep analytic properties of these systems of PDEs. So assuming that your characteristic variety is cut out by polynomial equations, which is indeed the case that we're interested in, the dimension of the characteristic variety can be measured using the degree of the Hilbert function of its associated graded ring. right? We'll know that the Hilbert function is, assuming it's finitely generated, eventually polynomial. So holonomicity in this context can be kind of understood as a growth condition, right? Perhaps there's some way to understand holonomic in terms of how some nice filtration or some nice grading grows. So in terms of D modules, let's make that precise. I know we're being a little bit vague. We have the following theorem that describes exactly what the class of holonomic modules are in a nice kind of growth condition context. So start by taking your ring of differential operators over a polynomial ring in invariables. Q doesn't matter. You can have any field of characteristic 0, but the fact that it's a polynomial ring does matter. If you want a holonomic condition, even over different classes of regular rings, you have to be careful. So let BI be the filtration on D by total degree. Okay, so BI is going to be the K linear or Q linear, I guess here, span of all monomials of degree at most I, where the degree of a differential monomial, X to the alpha, D to the beta, here alpha and beta might be multi-indices, is the sum of all the alpha coefficients plus the sum of all the beta coefficients in those exponent vectors, okay? So basically, to measure the degree of a differential operator, you don't just look at its order, which is the betas only, you look at its degree where the x's also contribute. Well, if we have a filtration, we can take an associated graded ring, and it may not be obvious, but it turns out that this associated graded is a commutative Noetherian ring. It's actually just a polynomial ring in 2 invariables. Analysts would call this the ring of symbols of differential operators, the sigma 1 through sigma n being the symbols of the partial derivatives. And if you give me a finitely generated D module, it turns out to admit a so-called good filtration, which I'll define later, compatible with this BI filtration, B for Bernstein. It is called the Bernstein filtration. Such that the associated graded, which is a finitely generated module, so good filtration means the associated graded is finitely generated over the associated graded ring. And the Hilbert series of that associated graded looks like some rational function, polynomial A of t over 1 minus t to the d, 1 minus t to the n, where I'm being deliberately obtuse by separating these two parts. So D is some integer that ranges between 0 and n, and A is some polynomial. Both D and A of 1 turn out to be invariant if gamma is replaced with any other good filtration. So there's kind of a meaningful dimension that we can associate with the D module, and there is an invariant called the multiplicity that can be associated in terms of this filtration. So the D equals 0 class is the smallest possible, and those are the modules that are called holonomic. And that turns out to be a very stable property, right? If a module is holonomic, so are all of its submodules. If I have a map between 2 holonomic modules, the co-kernel is holonomic. And we kind of talked about some of the niceness properties of holonomic. So from this lens, holonomic corresponds to the growth of the Hilbert function being as slow as possible, where as slow as possible is non-trivial, right? You can't get anything in the denominator lower than that 1 minus t to the n. You can just get rid of this extra stuff. So holonomic is the D equals 0 class, okay? What are we going to do within this talk? Well, our immediate goal is to try to find a notion of holonomic for F modules that looks more like a minimal dimension type condition, possibly understood in terms of some Hilbert series achieving a minimal denominator, okay? In the long term, what we would want is something like the following. So it turns out to be easier to define a Bernstein filtration for the ring of Frobenius operators than for the ring of differential operators when R is singular. And the reason for this is somewhat simple to explain. If you give me a ring and want its ring of Frobenius operators, I'll tell you what I'm going to do. I'm going to adjoin a formal symbol and impose some commuting relations. So the presentation is kind of handed to you right on its face. However, if you give me a ring and want its ring of differential operators, I suppose I should say give me a K algebra and ask for its differential operators over K. There is no, to the best of my knowledge, nice closed form description of how to get a presentation of this algebra. It's a somewhat abstract definition involving iterated commutator constructions, and it's not really clear what generators for the module would be, or generators for this ring would be, other than the trivial, well, the ring is it generates itself, right? The whole ring is a set of generators, I guess. And I don't even believe it's known whether it is necessarily a finitely generated algebra over K. In fact, I think there are cases where it is known to not be that. So since we have a more explicit presentation for Frobenius operators, it is easier to try to do a Bernstein-like thing, modulo some difficulties that are the main subject of this talk. What should the degree in a Bernstein sense of a Frobenius monomial be, and does that degree have any nice properties? So a hope that we might have is, might a notion of holonomic based on the growth of Bernstein compatible filtrations fare a little better for F modules over singularities than the analogous notions of holonomic would fare over D modules? We already know from that kind of close support table that there are cases where we're able to get better mileage from characteristic P conditions than the analogous characteristic 0 ones. So is it possible that something like this might work? But broadly speaking, our interest is, are there other niceness things that we can staple onto finite generation that aren't just unit? And maybe holonomic is the way to go, maybe it's not. But maybe if we understand holonomic well enough in the regular setting, we might be able to, in the long term, make some progress on the singular setting. Okay, so if you would like, you can put that aside. The discussion of local cohomology will not come up again for a bit, and we can talk about just how do we even approach this concept of a Bernstein filtration? How do we measure the degree of Frobenius monomials, and how does that degree behave? So let's start with just an example. This example is going to correspond to behavior and characteristic 2. Just think about all strings in two non-commutative variables, x and f, where they obey a commuting relation. X squared f is equal to fx. Okay, so you have the ability to pass an x through f by doubling the number of x's. Let's define the complexity of a monomial to be the length of the smallest word in the symbols x and f that represents it. So for example, the complexity of xxf is 2 via the word fx. The complexity of 6x's followed by 2f's is 4 via the word fx. And you can imagine playing this game where I write down an arbitrary string involving f's and x's. You apply a list of simplification rules, and whatever the shortest thing is that you arrive at, where it can be simplified no further, will be the complexity. So for a fixed index I, how many monomials have complexity I? Counting this question for like commutative polynomial rings is easy. The growth is polynomial. Here it's maybe a little bit less obvious how the count is going to behave. And if you were starting with this, I think the first thing that you would do is just try to hook it up to a computer and see what you get and try to observe if there are any patterns. So suppose you did that and hooked it up to a computer and that's what you get. Well, in complexity 0, there's exactly one monomial, I guess, by convention, 1. In complexity 1, there are 2, x and f. In complexity 2, there are 4. There's the 3 obvious ones, along with fx, which is the same as x squared f. And if you saw nothing past this point, you might think, oh, so is it going to be like always a power of 2 or something? The answer is no. Once that fx is removed, you've also removed xxf from consideration under things of complexity 3, so you only get 7 monomials of complexity 3. You can check that all of these do in fact have 3 as their complexity. And it gets more complicated as you move forward. So in complexity 4, there are 12 monomials. And in complexity 5, there are 20 monomials. It's too big to fit on this slide, but in complexity 6, there are 33. In complexity 7, there are 54. And in complexity 8, there are 88. Okay. So this is, if we want to call it the Hilbert series for our filtration on monomials that we're trying to define or I guess Hilbert function in this case, this is how the Hilbert function looks. So how do the coefficients of the Hilbert series, or how does the Hilbert function tend to grow as I goes to infinity? Well, write down this list of monomial counts and study it for a bit, and you'll notice a pattern pretty quickly. So it's not polynomial growth, but it's also not the worst kind of growth you can imagine. Namely, this satisfies a relatively straightforward linear recurrence relation. So 2 times 4 minus 1 is 7. 2 times 7 minus 2 is 14, or sorry, 2 times 7 minus 2 is 12. 2 times 12 minus 4 is 20. 2 times 20 minus 7 is 33. 2 times 33 minus 12 is 54. And then we're past the capabilities of my mental arithmetic, but you can check that that does indeed continue to hold for 88 and 143. And if you ask the computer to iterate this up to degree 50, it will continue as far as you're able to check. So we have a sequence that satisfies a linear recursion. And just to be able to talk about linear recursions, let's set up the following convention. So suppose that you give me a right infinite sequence of integers. I'm going to let the ring Z adjoins sigma act on it by left shifting. So all of the terms move to the left and the A0 term falls off and goes away. So if you give me a polynomial P of sigma inside of this ring, we're going to say that your sequence satisfies the recursion P of sigma if when I apply that polynomial, I get 0 under the left shifting action. Okay, so the polynomial annihilates it. We could ask about like the annihilator, like the ideal of all polynomials that annihilate it. But for now, we're just going to talk about, does it satisfy the recursion or does it not? So in this polynomial, the recursion that we were describing is sigma cubed minus 2 sigma squared minus 1. So if you shift to the left 3 times and then subtract off twice the double shift left minus the original sequence, you get exactly the 0 sequence. Note, by the way, that using this polynomial convention, we can notice some kind of fun structural properties. This recursion here turns out to factor as sigma minus 1 times the Fibonacci recursion, which is kind of neat. So does this hold in general? Well, let's take our ring of Frobenius operators now in any characteristic P, not just 2, and in any number of variables, not just 1, which has the presentation that we discussed before. You adjoin a symbol F and impose some commuting relations via P powers. It is a theorem of Dils and Askew that this does satisfy a linear recurrence relation. So the Hilbert function that counts the number of monomials of complexity exactly I satisfies this recurrence relation. Sigma minus 1 to the n times some weird polynomial that I'm not going to read out loud, which has degree n times p minus 1 plus 1. And to give just a couple examples of how this looks, you can see kind of what forms this weird polynomial takes. If p equals 2, n equals 1, we see that we have the 1 sigma minus 1 term, and the weird polynomial is the Fibonacci recursion. If p were equal to 3, we get a sigma minus 1 and then a kind of generalized Fibonacci recursion where you add the previous 3 terms. If p equals 2, but we had 2 variables, you get something that looks like this as the weird polynomial. And notice that there's 2 of the sigma minus 1s and so on. So, okay. Let's say that we take our filtration by monomials of this complexity, which we now know how it grows, at least on the ring of operators itself. It grows like a linear recurrence relation. And we try to do the thing that we do when we have a filtration. We take the associated graded and ask what happens. So I'm going to let boldface A denote the associated graded ring of F with respect to P. So that's just the direct sum of all BI mod BI minus 1s, right? The symbols like the monomials of degree exactly I, and then if you multiply 2 things of degree I and degree J, and the result ends up having degree less than I plus J, it ends up being 0 in the associated graded, and so on. Okay. We're going to use just as notation bracket sub I to be the image of a element M inside of BI mod BI minus 1, assuming M has complexity no more than I. So this is what you might call the symbol in the language of filtrations, where note that this is 0 if the complexity is strictly less than I, but okay. What kind of properties does this ring A have? Remember that in the D module world, the associated graded of the ring of differential operators D with respect to the Bernstein filtration B turns out to be a commutative Noetherian ring. In fact, it's nothing more than the polynomial ring of 2 invariables. So here, again, ring structure being defined like normally for the associated graded ring. Here, first of all, note that we do not get a domain. If I take x squared, its symbol, which has degree 2, that's not 0, times f, its symbol has degree 1, that's not 0. I get x squared f degree 3, but x squared f is the same as fx. So its image in B3 mod B2 is 0, since it has complexity 2. There's another example of something that gives 0 when you multiply two non-zero elements. So we should not expect a domain. It's also not commutative, right? XF is still not equal to FX, even if you are killing some elements for having the wrong degree. We've seen that it is not a domain. And it is also not left Noetherian. So the ideal, or left ideal, I should say, generated by XF to the I for all I is not a finitely generated ideal. So essentially all of the nice properties that hold for the associated graded of the Bernstein filtration on D modules don't hold for the associated graded of the Bernstein filtration of F modules. Not commutative, not a domain, not Noetherian. So that might seem like we have cause to be very pessimistic about this object being useful, but if you play around with it enough, it's actually surprisingly not as bad as it would initially appear. Let's give some examples of that. So we're going to take a look at some graded left A modules that I claim are closely related to the associated gradeds of some F modules that we care about from local cohomology, although that relation is not going to be obvious at face value. First off, let's look at A mod the left ideal generated by X and XF. So all of these monomials we're just going to be modding out, or sorry, all of these examples we're going to be modding out by a monomial ideal, a left monomial ideal to be exact. Okay. So here we start with our list of all monomials in the X and F, and we kill all left multiples of X and then all left multiples of XF. So what does the Hilbert function of this module look like? Well, let's go through and count the monomials of different degree. We get one thing of degree 1, one thing of degree 0, one thing of degree 1, one thing of degree 2, two things of degree 3, three things of degree 4, 5 things of degree 5, and then it doesn't fit on the slide, 8 things of degree 6, 13 things of degree 7, 21 things of degree 8. And if you're looking at this Hilbert function, you'll notice that this does not look like a random sequence of integers. This looks like it has some structure to it. Maybe it's a coincidence. Let's look at this example. Here you're killing F, X squared F, and X to the 4th. Again, I promise this has some relation to a module that we care about in local cohomology theory. So first we'll kill all left multiples of F. And again, these are multiples in the associated graded ring. That's why it doesn't go all the way to the right when you're multiplying on the left. If you multiply by m by a high enough power, it eventually commutes through the F's, and then the complexity drops and you start getting 0. So you don't get all the way to X squared F with left multiples. So you kill all multiples of F, kill all multiples of X squared F on the left, and then all multiples of X to the 4th. And go through and count degrees. So we get one thing of degree 0, one thing of degree 1, one of degree 2, 2 of degree 3, 3 of degree 4, 5 of degree 5, then 8, 13, and 21. And now let's take a look at this. So again, kind of a strange collection of monomials here, but we'll go ahead and compute the associated graded ring anyway. So kill all left multiples of XF. Again, the fact that we're working in the associated graded, which is not a domain, is why the shape of that left ideal is kind of strange. Then kill all left multiples of X squared F, then all left multiples of X to the 4th F, and then all left multiples of X to the 5th. And what remains? Well, one thing of degree 0, one of degree 2, or sorry, 2 of degree 1, 2 of degree 2, 3 of degree 3, 5 of degree 4, 8 of degree 5, and then the following numbers are too large to fit on the slide, 13, 21, and 34. So in all of the cases, we get a list of numbers that is definitively not the Fibonacci sequence, but which eventually settles into the Fibonacci sequence, right? This starts off with some 1, 2, 2 stuff that does not satisfy the linear recursive relation, but eventually it settles into something that does. And is that really that concerning to us, right? If you think about the case where we're dealing with Hilbert functions of finitely generated modules over a polynomial ring, we don't always get something that is always a polynomial function of the degree. We get something that is eventually a polynomial function of the degree. So maybe the fact that this is only eventually linear recursive is not the biggest deal in the world. Okay. One way to think about eventual linear recursions on the Hilbert function is in terms of denominators of the Hilbert series, right? If I am telling you that some left shifting combination of the sequence will get you to 0, then I'm also telling you that if you were to write out those sequence as coefficients on powers of t and multiplied by an appropriate polynomial in t, then if it exactly satisfied the relation, you would get 0. And if it eventually satisfied it, you would get a few low powers of t left where it hadn't quite settled in yet. Then just divide out by that polynomial you multiplied by, and you get that you have a rational function. So the Hilbert series of the associated graded itself in our example has coefficients 1, 2, 4, 7, 12, 20, 33. And in terms of the Hilbert series, the denominator is 1 minus t, 1 minus t minus t squared. For the first two graded modules that we looked at, A mod the left ideal x and xf, and then A mod the left ideal f, x squared f, and x to the fourth, our coefficients were 1, 1, 1, so not quite Fibonacci yet, then 2, 3, 5, 8. So we get something that looks like this, where we have the smaller recursion in the denominator. And then for the one who's killing xf, x squared f, x to the fourth f, x to the fifth, it was still eventually the 1 minus t squared recursion, but it had more weird stuff going on at the beginning before it settled into it. And as a result, the Hilbert series ends up with some weirder stuff in the numerator. But in any case, we end up with rational looking Hilbert series where the denominators somewhat resemble the denominator of the original one, the ring of operators, except for being a little bit smaller, lacking this 1 minus t thing. So this turns out to not be a coincidence. Let F be the ring of Frobenius operators over Fp. Here again, I'm not really harmed by faithfully flat base change if you want a different field of characteristic P, where you have that commuting relation by pth powers. And let Bi be the quote unquote Bernstein filtration, where you are filtering by monomial complexity. So we're going to let A be the associated graded ring of F with respect to the Bernstein filtration. So this is the thing that in D module world would just be a polynomial ring and 2 invariables. And for us is a non-commutative, non-Noetherian, non-domain kind of thing. Well, somewhat surprisingly, we actually still get some pretty nice behavior. If you were to take a finitely presented graded A module, the Hilbert series will always have the following form. So there is some polynomial in the numerator, and in the denominator, you have one polynomial that's determined by the Dils NSQ recursion and some power of 1 minus t. That power can range anywhere from 0 to n. So if you compare and contrast with what the Hilbert series looked like in the D module setting, we have some numerator, some power of 1 minus t that ranges from 0 to n, and then some other stuff, which in the D module world was 1 minus t to the n, and in our world is some weirder looking polynomial that is sometimes a Fibonacci recursion and is sometimes something weirder. This still carves out a minimal class, right? The slowest growth, quote unquote, is going to happen when you set d equal to 0. That's kind of the minimum class in terms of the denominator. And by possible abuse of terminology, kind of trying as hard as we can to mimic the D module characteristic variety world, we could try to think of D as being analogous to a dimension of sorts. We could think of D equals 0 as carving out the graded A modules that are as small as possible. And it might be possible to view A of 1 as a kind of multiplicity. Emphasis on might be. If it's going to be called a multiplicity, it should be independent of filtration, which is not something that we know yet. So this is something that we might hope for, but we do not know whether it deserves the name invariant at this point. But what I want to talk about is why we know this to be true. We're working over quite a nasty ring. So how do we end up with something this somewhat reasonable looking as the Hilbert series? Well, so if you don't have access to all of the kind of abstract high power tools, you're left with attempting kind of direct computation, which is, I mean, the historical origin of some of the abstract high power tools in the first place. try to set up a term order, try to manipulate things in terms of their initial terms, and try to describe syzygies in terms of syzygies on the initial terms. Now, getting a term order on Frobenius monomials is going to be a bit tricky, but we can try it. Let's just set up some notation first. So I claim that every monomial in A can be written uniquely in the following form. Here, x to the v, f to the e, x to the r is obtained by taking as many powers of x as you can possibly commute through f to the e, and then commuting them through to the other side, while leaving whatever is left over behind on the left side of the f to the e. So the x to the v consists of exponents on the x's that are all strictly less than p to the e. If it was greater, you should commute it through to the other side. And I'm going to let vi be the sum of all of those treated as base p digits. So fix the ith monomial and then add up all of the different Vij things that we get. So here, x to the r is everything that we get commuting through the, oh, sorry, I completely misspoke on that. My apologies. Vi is some integer, write it out in base p. Vig are defined to be the base p digits. I'm not stringing anything out of the base p digits. This is just how those Vij notation is defined. My apologies. So x to the r is whatever you get when you move everything you can past all of the f's. And once you've put it into this standard form, how do you measure the complexity? Well, here's where that Vij notation comes in. The complexity of this monomial turns out to be the number of f's, e, plus the sum of all of the r's, plus the sum of the base p digits of all of the vi's. So take the leftover stuff on the left of the f's, write them in base p, take the digits, and then add up the digits. And that ends up being what the complexity comes out to. So E, we're going to call the F degree of the monomial. And X to the R, just to have notation to call it by, we're going to refer to as the carriage. It's being like carried past the F to the E's on M, where the X to the V, F to the E will refer to as the prefix of the monomial. So just some things to be aware of in terms of manipulating monomials. If M is a monomial, then first of all, left multiplication by F is injective. That is nice because we're not in a domain. So multiplication by F can never kill a monomial that was not zero to begin with. Second is that if a monomial has any F's at all, then left multiplication does not change the carriage. So this X to the R part is kind of fixed for all time. You can multiply by whatever you get. It might kill it and you get zero. But if the result is non-zero at all, that X to the R is unchanged. Why is that? Because if something can commute through the X to the E's, or sorry, through the F to the E when you multiply, that commutation will drop the complexity below what it's supposed to be in the associated graded and give you zero. So kind of necessarily has to not change. And then the other thing to note is that if your degree on F is positive, then there's a sufficiently high power you can multiply by for each variable xi in order to get zero. Why is that? Because if I multiply by enough x's, eventually they will commute through the F to the E, right? If I commute through at least, or if I multiply by at least P to the E of them, that will drop the complexity below what it's supposed to be in the associated graded, and I end up with zero. Okay. So that's our convention for writing out monomials. I know it's a bit of a mouthful, but how are we going to put an order on these things? Where again, we want term order to preserve the degree. Well, the trickiest part is going to be having our term order work with the prefixes, that X to the V thing. We have to do something a little bit kind of weird with the VI exponents. Namely, we're going to order them reverse lexicographically on their base P digits. So I'll give the definition if you want to see it. The P revlex order on natural numbers less than P to the E is you find the largest index, or sorry, the first index J, at which the two of them agree for all I strictly less than J, and at the jth position, If uj is greater than vj, then you flip the equality and declare u to be smaller in p revlex. So it's just the definition of revlex that you would see anywhere, but revlexing the base p digits. But I think it's easiest to just show you an example to see what revlex is doing that's different from the usual order on natural numbers less than 8. You're taking the base 2 digits, in this case p equals 2. And if you read it backwards, it's in incrementing order, right? 0, 1, 2, 3, 4, 5, 6, 7. And then we flip the direction of the inequalities. So written out in base 10, it looks a little bit weird. 7 less than 3 less than 5, 1, 6, 2, 4, 0. But since the complexity cares more about the base p digits of these, right? Because you're kind of commuting as many powers of p through as you can at a time, and like these chunks that are separated by f symbols, it maybe makes sense that it would work better if we looked at the base p expansion of these than at the base 10 expansion. Okay, without further ado, what's the term order that we're going to use? So graded reversal X order on monomials in A is going to be the following relation we'll define. If you give me two monomials, X to the U, F to the D, X to the S, and X to the V, F to the E, X to the R, we're going to declare the one with the beta subscript, complexity beta, to be bigger than the one with the alpha subscript whenever any of the following conditions hold. So think of this like a checklist. First and foremost, if your complexity is higher, you automatically win and you are bigger in the order. So this order, by definition, preserves the grading. If the complexity is tied, then the next place you're going to look is the F degree. If you have more Fs, then you automatically win. Nothing else you have to check. You only descend to this bullet if you have the same complexity and the same number of Fs. And what you're going to do in this case is you're going to look at the prefix, that X to the V and the X to the U. You're going to find the first variable where those prefixes disagree. And assuming they disagree at all, if they don't ever disagree, move to bullet 4. But assuming they disagree somewhere, you're going to find that first position of disagreement and do P revlex on the exponents of that X to the I. Or sorry, on that X of I. I'll show you an example of how that looks on the next slide. But assuming that the complexities are the same and the number of F's is the same and the prefixes are identical, then just do grevlex on the carriages, right? You have these X to the R, X to the S's, and then do grevlex. It doesn't even matter that this is grevlex. You could do like gerlex or whatever. Just order them in some way at this point. Okay. So most important thing is that this refines the order by complexity, and after that refines the order by F degree. Okay. The other thing that I will note is that there is an obvious extension to free modules. You could either do order by the position in a vector in the free module, then by monomials, or order the largest monomial and then break ties with position and that kind of stuff. There's sort of general considerations you have to think about when you're trying to extend a monomial ordering to free modules. This one, you can do much the same thing. Okay. So let's look at an example. If P is equal to 2 and N is equal to 1, we can order the monomials of complexity 6 and F degree 3, right? So we're assuming that you've tied on complexity and you've tied on F degree, and now we have to break ties somehow. Well, okay. It's going to look a little bit weird if you write it out in base 10, X to the 7, X to the 11, X to the 13, all right, 17, 14, 18, 20, 48. It makes more sense if you write them out in the standard form and then put the prefixes in base 2, where what you'll notice is that we are just exactly doing P revlex on the exponents for the X's. So we have all zeros, then 1 written backwards, 2 written backwards, 3 written backwards, 4 written backwards, 5 written backwards and forwards, so on and so forth, 6 written backwards and so on. In that case, that successfully orders everything because we only have 1 variable, so we don't have to look at the carriages. If there were extra variables, we would have to break ties there too, using grevlex. So you might have multiple X to the 101 F cubed vectors and then, or sorry, monomials, and then you would order like by looking at X and then Y, or Y and then X, depending on which variable you want to privilege.
Can I hold you off on for a second? We usually end after an hour and a half, but I think I got the impression that maybe you didn't realize that.
Oh, sorry.
No. So what I propose is that if people need to go, they can, but I propose you continue and we record it because I think it's worth doing. And I'd like to hear it.
Okay.
I don't know
Yeah,
how much more you had.
Yeah, my apologies. I'll kind of skim through some of the technicalities there to kind of get to the punchline then.
Sure, sure.
So the upshot of this is that it behaves like a term order. So if A is less than B, and then you multiply by some C, assuming the results are both non-zero, then CA is still less than CB. Hilbert's basis theorem is still, Macaulay's basis theorem is still true. The monomials that don't belong to the initial ideal are a vector space basis for the, or initial module, I guess, are a vector space basis for the quotient by that module, and this refines on a degree by degree term. Hilbert functions are unchanged if you degenerate to initial submodules. And if you have a containment of two modules that have the same initial ideal, then the submodule has to be the entire module. So we get the behavior that we would expect from a term order. I will make as a comment that something that deserves to be called Buchberger's criterion still holds about lifting initial terms of syzygies to syzygies on initial forms being a criterion for whether something is a Grobner basis, or Grobner basis means that the initial terms generate the initial module. And I won't give too much of an indication of why Buchberger's algorithm here works. I will just mention that it does. But the important thing is that there is an explicit Buchberger's algorithm that you can carry out. And while you're carrying it out, the F degree turns out to never increase because you can explicitly classify monomial syzygies and just show that that is the case. And the carriages never change by left multiplication. So between those two facts, you can put together something that resembles Dixon's lemma, telling you that if you have bounds on carriages and bounds on F degree, then any monomial ideal is going to be finitely generated. And once you have a Buchberger's criterion-ish and a Dixon's lemma-ish, then you end up with something that kind of resembles the punchlines, where a finitely generated submodule is going to have a finitely generated initial submodule. So the Buchberger's algorithm stops after finitely many steps because of Dixon's lemma. And it's necessarily finitely presented because Buchberger's algorithm, as a side effect, incidentally computes the syzygies on the set, not just the initial submodule. So we get that we have a finitely presented submodule as well, which is kind of cool. So to prove the result on Hilbert series from this, what do you do? Well, first of all, you can degenerate to the quotient by the initial module instead of the original module. That doesn't change the Hilbert series at all, so you only have to deal with monomials. And of course, if you're taking a free module and quotienting by a monomial submodule, you can just work with each of the individual factors. It's really just quotients by left monomial ideals that you have to understand. And those can be explicitly understood enough that you can show that they admit finite graded free resolutions by finite rank free modules, because we understand how monomial syzygies work in this ring. So once you have a finite graded free resolution by finite rank A modules, all you have to do are take alternating series or alternating sums of the Hilbert functions of the terms of the free resolution to get the Hilbert function of the thing that's being resolved. So what that corresponds to for Hilbert series is various t to the I shifts of the Hilbert series of the associated graded ring. That latter Hilbert series is known by Dills and Askew. So the result ends up following at once you're just taking an alternating series of all of those. So it's basically the same way that we understand, or at least one proof of how we understand Hilbert series in the polynomial case. We know the Hilbert series of the polynomial ring itself by explicit combinatorial arguments. We know that arbitrary finitely generated modules have finite free resolutions. And if we're in the graded setting, those free resolutions can be graded. So alternating sums of the Hilbert series with appropriate shifts give you the Hilbert series of the module that you're resolving. Okay. So just to wrap up and show what the modules on the original kind of beginning of this talk were. The first one is you take local cohomology with respect to X and form its associated graded and then passed to the quotient by the initial submodule. And that ends up belonging to our minimal dimension class, the d equals 0 class. Its free finite graded free resolution looks like this. The second one was taking the polynomial ring itself as an F module, passing to its associated graded, then degenerating to the quotient by its initial ideal. That was this one. It has the following graded free resolution and has a Hilbert series that puts it in our minimal dimension class. And then the last one was the localization at the localization at X, which if you take its structure as an F module, form is associated graded with the Bernstein filtration, and then pass to its initial submodule, we ended up with this object. The free resolution looks like this, and the Hilbert series puts you inside of the minimal dimension class. So all of these three modules that we would want to call holonomic, local cohomology, the ring itself, localization at one element, end up in our minimal dimension class. So what remains an open question is getting this to carry over in general. So I believe that without too much effort, and I'm not going to state this confidently yet because this much is not written up, that localizations of the polynomial ring at a single element we can get inside of the holonomic class, although I am not as confident about if you take a holonomic module, meaning minimal dimension, and localize it, that holonomicity will be preserved. And the other big thing that is still missing before we can really say we're confident this is the right notion of holonomic is we need to know more about invariance under change of filtration. So it would be really nice to have a theory of multiplicity for F modules, but it only deserves to be multiplicity if that does not change when you pass to another good filtration, where good here means finitely presented, not just finitely generated. And likewise with the dimension, you would want that to be a filtration invariant thing. Some of the things that we saw, like the Betti numbers of the associated graded, are probably not filtration invariant, though it would be cool if they turned out to be. But more needs to be understood about filtration invariance before we can say super confidently, whether this theory of multiplicity should work or not. But long story short, to kind of wrap up the conclusion, it looks like it is going to be possible to do something like the Bernstein class kind of notion of holonomic for F modules over a polynomial ring. This is capturing a lot of local cohomology adjacent modules that we care about. It may capture all of them, we don't know yet. This is very different from unit. So if it fails for singular rings, it's at least got to fail for a different reason. And if it does, that would be really interesting to know what it is. But yeah, there's still a lot of kind of interesting things that we would like to ask about it. But we are out of time, so I'll go ahead and wrap up. And thank you very much again to the organizers.
Thank you for a really, really good talk. Thank you. So let's thank Monica. And are there any questions? Please go ahead. You can just unmute. Mm-hmm.
I have a question. Thank you very much for the very nice talk. I would like to hear a few words, if you can say, about how to think of a module that is an finally presented A module for your associated graded ring in relation to the original polynomial ring. Is there any? For example, if I take a quotient of the original polynomial ring, can I make it an A module? Would A is your graded ring, or that's probably?
Just to be clear, by quotient of the original polynomial ring, do you mean quotient of the ring of operators F, or like quotient?
No. In the Frobenius, you just take the polynomial ring x1 extended mod out by some equation.
Oh, I see. I'm trying to think. I computed one example of this, and its Hilbert series did not look like the finally presented case. I think it ended up not being a finally presented A module. Okay. yeah, like if you take like R, like take the polynomial ring adjoining a bunch of variables and then kill some random polynomial and then treat that as an F module. Right, and we kind of know that that can't always work, because if we go back to the original
Right.
statement, this GPN depends a lot on what N is, but I could look at like FP adjoin X as an FP adjoin XY module just by killing Y. And its Hilbert series definitely like does not have this form, because it will have like the
Yes.
different kind of recurrence in the denominator. So yeah, the quotients are, it's not out of the question that they might have
Okay.
some other like recurrence that they always have to satisfy, maybe more complicated than the GPN thing, but I don't know.
Thank you very much.
Any more questions? In the differential operators world, I mean, in characteristic zero, it's also hard to take quotients and make them into modules, because the ideal doesn't tend to be preserved.
Right.
Yeah,
Right, I
but
guess then,
How very different, because you're measuring
yeah.
sizes, yeah?
Yeah, I mean, I guess the enticing thing about the Frobenius setting is that like almost no ideals are D stable, but all ideals are like trivially F stable. So it like seems like there might be more leeway in like trying to
Yeah.
get like good F module structure for those, but it fails for like kind of weird subtle reasons. Whereas in D modules, I guess you just can't even get up off the ground, because if you kill an equation, that equation, the ideal it generates is not a D submodule. So you have to take differential operators over the quotient, and then that opens like a whole can of worms, like Bernstein, Gelfand. Yeah.
Yeah, it's really interesting. More questions? No. Okay, so let's thank Monica again. And thank you for a wonderful talk.
Thank you.